Hey everybody, it's Friday the 23rd. Little impromptu video for you today. Didn't have this one originally planned at all, but after a question about one of the personal progress check questions in the morning meeting, I figured I wanted to make this video. The short of it is somebody asked a question in the morning meeting about a question on the personal progress check that had this diagram in it that I gave what I would consider to be an unsatisfactory answer to. And you really can't understand this question at all unless you understand a lot of details about a vertical spring oscillator. And so that's what I want to talk about here in this video. This video is hopefully going to be on the shortish side. Of course, I want to make sure I am explaining this as clearly as possible. So let's just jump right into it. The thing that's annoying about a vertical spring oscillator is it seems very different from a horizontal spring block oscillator. So the first thing that we should say is one of the biggest differences between these oscillators is what's happening at the equilibrium position. At the equilibrium position for a horizontal block oscillator, this is the place where the spring force is equal to zero. That's what makes it the equilibrium position. Of course, equilibrium in the context of a simple harmonic oscillator means the exact same thing as the normal definition of equilibrium. The net force is zero. And for this object experiencing this horizontal simple harmonic motion, the only force acting on it is the spring force. And so that's where the spring force is equal to zero. Now the net force is zero. What we're also going to say here is that because the spring force is directly proportional to the displacement, the spring force being zero means x is equal to zero at this particular location. That's the natural length of the spring. And so what we're saying here is because the x is equal to zero and because the spring potential energy is directly proportional to x squared, at the equilibrium position for a horizontal spring, the spring potential energy is equal to zero at the equilibrium position. Because at the equilibrium position, the spring potential energy is equal to zero, that means all of the total energy there is just kinetic energy. And so the maximum speed given there is square root of k over m times a. That's what you get if you set 1/2 ka squared, the total energy, equal to the kinetic energy 1/2 mv squared. That's the deal. It's a simple conversion from potential to kinetic, and at the equilibrium position, because there is no potential energy, it's all kinetic, and so you get that equation. Now, of course, for the vertical oscillator, it's a little different because there is a natural spring length here, which we would call x equals zero, that this thing has. But when we hang a mass onto it, this thing is displaced down further. And so because this thing is displaced down further, we have a totally different situation happening at the equilibrium position. The equilibrium position is no longer the place where the spring force equals zero, because now we have to deal with the effects of gravity because it's not being canceled out by the normal force. So the defining characteristic of the equilibrium position, once again, is that the net force is equal to zero. But in this particular circumstance, it's the location where the spring force is equal to the weight. So the key detail here is that a major difference is that at the equilibrium position for the horizontal oscillator, the spring force equals zero, whereas for the vertical oscillator, the spring force does not equal zero. That said, this is not like a big catastrophe or anything, because we can figure out what that equilibrium position is. If we take kx, the equation for the spring force, and we set it equal to mg, the equation for the weight, then we can determine the location of that equilibrium position. It should make sense. It's going to be farther away from the natural length of the spring. If the object is heavier, that's because it's going to be pulling down the spring more. That makes a heck of a lot of sense. And it would be closer to the natural length of the spring for a larger spring constant, because a larger spring constant means a stiffer spring, which means that mass isn't going to pull it down as much. That's pretty straightforward. Now, I think the main thing to understand here, though, what makes this totally different, is that because the elastic potential energy is proportional to x squared, and now the equilibrium position is at an x value that's not equal to 0 like it was for the horizontal oscillator, the basic idea is the spring potential energy here is not equal to 0. And that is a huge, huge difference between these kinds of problems. Now, of course, what we really want to see is, well, how does this change the overall oscillation of the object now that what we are saying the equilibrium position is a location where the spring energy is not equal to 0? Like, does the fact that this thing is vertical change the nature of the oscillation or not? And we can use conservation of energy to figure that out. Basically, for these kinds of vertical oscillator problems, we have like 3 important locations. The first important location is just the natural length of the spring. The reason why that's important is because the equation for the elastic potential energy, 1/2 kx squared, is really based on this location. If it is stretched from that location, the x value will be some number, and therefore the thing will have elastic potential energy. We also have the equilibrium position. That's an important location. This is just where the mass is hanging from the spring, but not actually oscillating. And then we have the location where we actually displace the spring from the equilibrium position and allow it to oscillate. So essentially what's happening in this diagram is this thing is just sitting here naturally. We pull the thing down, and then the system is going to oscillate. Now, I want to make this not confusing. And so this, these definitions in this diagram with a delta x and x prime and x, those are way too easy to confuse. So let's just go ahead and call this distance A. A now is going to be the distance the spring stretches from the natural length of the spring when it's at its equilibrium position. We'll go ahead and call this distance B. B is effectively just going to be the distance we pull the thing back in order to set it into oscillation. This is when we're doing the work. Remember when we were first talking about this, I always referred to like the work period. That would be us pulling the thing a distance B to do work to set the thing into motion. And so now, according to this diagram here, this value is just going to be A plus B. And so what we would like to do now is we'd like to be able to derive an equation for the maximum speed to see if there's really any difference. And so let's do that now. Notice I've just put this diagram up in the corner, and I've labeled my variables like I did in the last picture, A, B, and A plus B. So the first thing to realize is that because this is a vertical oscillator, we now have to deal with the fact that gravity is involved in the situation, and there's going to be gravitational potential energy. It always made sense when we were talking about gravitational potential energy to call the 0 height the place where the lowest point in the system exists. And that's when the object is all the way down here. So we're going to measure all heights relative to the lowest point this thing ever gets, which is this line right here. And so like we said, we need to apply conservation of energy. The only thing I want to do here is just extend this line over and remind you, this is the equilibrium position. So what we are going to do now, because again, the whole point of this is figuring out what Vmax is to see if the nature of the vertical nature of the spring actually changes the situation, is that's where the velocity is maximized at the equilibrium position. So that's going to be a relevant point here. We got to apply conservation of energy. And the whole time we're doing this, it's important not to lose sight of the fact that we are basically just considering the motion of this object from here to here. because it's going from the amplitude to the equilibrium position. And the equilibrium position, of course, is where our velocity is maximized. So at the amplitude, this thing just has an elastic potential energy. That's important to realize. And the elastic potential energy is generally given by the equation 1/2 kx squared. But even before I go on to the other side of this equation, just so we don't lose the thread here, we have to be very careful about what we say x is. X is the change in the spring length from its natural length. And so that value here is going to be this distance plus this distance. And so that value is A, and that value is B. And so we're going to say here that X in this particular instance is A plus B. And of course, we've got to square it. And so we'll put that in there as A plus B squared. Now, the final energy that we have here is going to be a bit tricky. And that's because there's three kinds of energy there. The kinds of energy are elastic potential energy, because notice, even when the object is here, it's still some distance from the natural spring length. In other words, the spring is still being stretched a little bit from its normal state. It's going to have kinetic energy, and that's cool because we're trying to solve for that V. And it's going to have gravitational potential energy. So now what we want to do is we want to sort of like reformat those equations to fit the variables and the descriptions we've already given to this diagram. So the first question is, well, what is the potential energy going to be at the equilibrium position? At the equilibrium position, it is at distance A away from the natural spring length. So that term is going to be easy. It's just going to be 1/2 Ka squared. Of course, the 1/2 mv squared term is not really going to change. We are solving for V. So that stays put. And now we need to figure out how much gravitational potential energy did this thing just gain? Because it was originally at the 0 height mark, which we said is this lowest point here. So it had no gravitational potential energy. And now it's gained gravitational potential energy moving between these 2 points. The height it just gained was B. And so because it gained a height of B, we're going to list that as mgb. The height it just gained is equal to this distance B, so the potential energy it has now is mgb. Now we have an annoying amount of work to do, because this squared term is a sum, which means we need to FOIL or distribute these terms, because remember, A plus B squared is really this. So we need to do the first, the outer, the inner, the last right here. So we have 1/2 K, and then we need to put parentheses. If we do the first terms here, that's going to give us an A squared. Then we're going to get AB, so that's going to be 2AB. And then, of course, the last terms is B times B, so that's going to give me a B squared. Okay. Then I have, of course, on this side, 1/2 Ka squared plus 1/2 mv squared plus mgb. I'm not doing anything to this side yet, because what I first have to do to really see how this is going to work is to distribute the 1/2 K. So I'm going to have 1/2 K times A squared. I'm going to have 1/2 K times 2AB. And I'm just going to put that in parentheses so I don't lose the thread here. And then I'm going to have 1/2 K times B squared. And then, of course, on my right-hand side, I'm going to have everything the same. 1/2 Ka squared plus 1/2 mv squared plus mgb. Now I'm going to change the pen color to red, because as annoying as that was and how many individual terms we have floating around, we've got some nice things happening here. The first nice thing happening, which I would imagine many of you realized the second I wrote it down, is that there's a 1/2 here and there's a 2 there inside that term. So those are going to cancel. What you should also realize is that I have a 1/2 Ka squared here and a 1/2 Ka squared there. If we subtract that 1/2 Ka squared to the other side, it's going to cancel. It's gone. And so now I've cleaned this thing up considerably. And so if we rewrite this now with our canceled terms gone, from this term left over, I have k times a times b. Then I have 1/2 kb squared. And then on the right-hand side, I have 1/2 mv squared plus mgb. That side hasn't really changed. The only thing we lost was the 1/2 ka squared because it canceled. Now, this term is gross. But there's something very interesting that we can apply now to clean this up. Because this Ka term here is actually relevant. Going back to the previous slides here, we said the equilibrium condition is that Kx, when the thing is at its equilibrium position, is equal to mg. Notice the x, when this thing is at its equilibrium position, is this distance a. So if we apply Kx equals mg and fit it specifically to this situation, that means Ka is equal to mg. And so I'm going to take my Ka and I'm going to substitute in mg. Now, some of you might be thinking, well, why in the hell would you do that? What's the point? Well, look at the line that I'm writing now. Do you see it? On the left-hand side of this equation, we've got an mgb. And on the right-hand side of this equation, we've got an mgb. And so it's very important to realize here what that is showing you is that once you do all of this crazy math, you just end up getting 1/2 k something squared, or let's call that x for a second, 1/2 kx squared equals 1/2 mv squared, and it looks like a regular conservation of energy problem, just like the horizontal oscillator. And so really what we're saying for a vertical oscillator, if we consider this to be our new equilibrium position for energy, then we can completely ignore gravity. The period is going to be the same. The maximum speed is going to be the same. In this case, this would just be b, because b is the new amplitude, where b equals the amplitude. If we call the equilibrium position, the place where the mass is bringing the spring down to, if we call that our new equilibrium position, nothing changes. And that's pretty cool. And so the main idea that we are trying to get across here right now is that this situation looks just like a horizontal oscillator, and mathematically we could treat it the same. Conceptually, we can treat it the same. Everything is the same. Notice here, if I hang this down, this mass on this spring here, and I show the mass equilibrium line, and I add this movable line here, notice if I put out this ruler and I really make sure I line up, let me just line up the 10 centimeter line because it'll be easier to talk about this here. If I make my movable line now sit at 20 centimeters and I displace this spring and the block 10 centimeters now to the 20 centimeter line, it basically is just going to move perfectly symmetrically around that line. Notice now, if I move this up, the midpoint, which I'll pause it when it reaches the maximum height here, the midpoint of the block, which is where we were making our measurements from, goes exactly the same height above the equilibrium line as we pulled it down below the equilibrium line. It is a symmetrical oscillation, and that's a really important point. If we pull it down 5 meters below the mass equilibrium line, it goes up 5 meters above that line when it's oscillating, just like the horizontal oscillator. If it moves in the positive direction, a distance equal to the amplitude, it moves in the vertical direction, a distance equal to the amplitude. And that brings us to this problem. In this problem in the personal progress check, which I think the first important thing to say is that there was a problem with this question. the answer choice was wrong. But it wasn't that wrong. And how you solve this problem is actually fairly important. It says here in experiment 1, a block of mass m is attached to the end of a vertical spring of spring constant k naught. I don't know why that's printed there twice. I guess it got reformatted when I copied it. With its free end at vertical position L naught as shown in figure 1. Now that's already a bad question the way I see it, because they're talking about this as being a position, and then they're giving it the symbol of length. And length and position are not quite the same thing. The mass of the spring is considered to be negligible. Obviously, if the mass was heavy, it would pull itself down with its own weight, and that would change things. So they're saying it's a massless spring. When the block is attached to the spring and it's at rest at the block's spring equilibrium position, the spring is stretched so that its end is now at position L1, as shown in figure 2. The block is then pulled down to a new vertical position L2 and then released from rest so that the block spring system oscillates. Assume that the reference line for zero gravitational potential energy is at the lowest point of the system's vertical displacement from equilibrium. The experiment is assumed to be performed near the Earth's surface. So notice here, they're setting this up the way that I just set it up here. They're saying, hey, that lowest point is the zero line for the gravitational potential energy. That's where your delta Y or your H, if you're still using that equation, is equal to 0. They give that line, this fact, like that's very important. But then look at the question. It says, what is the magnitude of the change in potential energy of the block spring system? They screwed us. The block spring system does not include the Earth. And because the block spring system doesn't include the Earth, gravitational potential energy does not factor into that. They screwed us. This is a confusing question. Let's make that perfectly clear. So now we have to really consider their phrasing here, the lowest vertical position to the highest vertical position. Now, this is the part of the question that I think is totally confusing, and you really have to think your way through it. It's important to realize, as we said, this oscillation is symmetrical. So the low point here, I think from the diagram, is pretty obvious. It's going to be L naught plus L1 plus L2, right? It's just going to be whatever this whole distance is. But as we said, the highest position is going to be basically the positive amplitude, if you will. And we said this oscillation is symmetrical. And so this L2 here, that this block goes below this line, this is like the distance it's pulled down to make it oscillate, it's going to go that distance L2 above that line. So how do you get that? Well, the way you get that is you think, well, this line here is L naught plus L1, right? This line right here is L naught plus L1. But if it's going to go L2 above that, then we need to take that off. And so the highest position then is going to be L naught plus L1 minus L2. Now, here's the deal, though. When we are considering the potential energy change, you have to realize that the L naught here is the natural length of the spring. The reason why that's important is because when the length is L naught, if we plug that into the equation 1/2 kx squared, the energy should be 0 there. That's an important thing. When the length of the spring is L naught plus L1, let's just say here, this thing does have a potential energy. But it has a potential energy only because of the L1 part. The L naught contributes 0 to the spring potential energy. The distances really are measured relative to that. And so the idea is, for the purposes of the potential energy calculation, because that contributes nothing to the potential energy, we can get rid of that term. And so now we're ready to solve this thing. It ends up being a total pain, but we can solve it. The first thing to realize is that we have to consider the system at its lowest point. So if we consider the system at its lowest point here, the equation 1/2 kx squared turns into 1/2 k times that distance that we had here, L1 plus L2. And then we've got to square that. Once again, this is going to be like a big FOIL job because we have something being added together in the square. And so we'll have 1/2 k times, and you know how this is going to go now. We're going to have an L1 squared. We're going to have a 2L1 L2, and we're going to have an L2 squared. That's the idea. That's the basic FOIL for these two terms. That's it. Now, of course, we're going to have to take the difference between these two values, and that's an important thing. And so first, we got to find the highest value before we can subtract. Now, the highest point is a little bit of an annoying part because when we take the 1/2 kx squared, we have to subtract 1/2 k times L1 minus L2. Because remember, we said the highest point is going to be that part subtracted off because it's going that far above L1. That's a crucial thing to understand. So once we square that, now we're going to have US equals 1/2 k. And I'm going to show this part just in case it's going to confuse anybody, because the whole point of this video is for you to not be confused about this anymore. And so we have L1 minus L2 times L1 minus L2. So we go first, and that gives us L1 squared, L1 times L1. Then we go outer, so that's going to be minus L1 L2. Then we're going to go these terms here, the inner terms. We have, again, minus L1 L2, and then we're going to have negative L2 times negative L2, so that's going to be plus L2 squared. So what that ends up giving us is L1 squared minus 2L1 L2 plus L2 squared. So that's going to be 1/2 k times L1 squared minus 2L1 L2 plus L2 squared. Now that I just looked up here at this top line, this square is not supposed to be on the outside of this parentheses. This is supposed to be here. Sorry about that. And so now you can see the differences between these. Because this minus sign was here, this is not that big of a leap, I don't think. Because this minus sign is here, it just changes that middle term from being a negative to being a positive. Okay. Now we have to subtract. The change in potential energy is going to be the difference between the potential energies as the lowest point and the highest point. That's what they asked us. Now I'm going to take the lowest minus the highest. And the reason why I'm going to do that is because the lowest has a bigger potential energy than the highest point, right? Because the spring is stretched more at the lowest point. And so I'm going to take just the bigger thing minus the smaller thing. So the potential energy at the lowest point is 1/2 k, 1/2 k times L1 squared plus 2L1 L2 plus L2 squared. Okay. And then we're going to subtract 1/2 k times, and notice it was that same thing just with the minus sign. So we have L1 squared minus 2L1 L2 plus L2 squared. And now I'm just going to distribute the k so we don't lose our minds. So we have delta US equals 1/2 k L1 squared plus, now notice the 1/2 times the 2 is going to cancel, but I'm just going to write them next to each other so we don't think we accidentally forgot about it. 1/2 times 2k L1 L2, and then I'm going to have plus 1/2 k L2 squared. Now, because I'm subtracting, I'm going to make this a plus and just call all the things that were positive negative and all the things that were negative positive. So this is subtracted also. And so I'm going to have here minus, because I have a minus sign here, 1/2 of k times L1 squared. So 1/2 k L1 squared. And then notice now, because this was negative and I was subtracting, this ends up being added. So I have plus 1/2 times 2 K L1 L2. And then this is subtraction here. So I have minus 1/2 K L2 squared. Now I can take out my red pen because I've got some modifications to make, some cancellations. I got a 1/2 KL squared, and I got a negative 1/2 KL squared. I got a 1/2 KL2 squared, and I got a 1/2 KL2 squared. I've got a 1/2 and a 2, and I've got a 1/2 and a 2. And so here, the answer is just going to be the change in the spring potential is equal to K L1 L2 plus K L1 L2. And that ends up making the answer, the change in the spring potential is 2K L1 L2. Now, as I mentioned, if you look at the actual AP classroom question, that is the answer shown, but it is not the result of the work. And I think that's an important thing to pay attention to as we're moving through this particular unit. Because if you look at the answer choice, there it is. But that's not what they show with the work. They made a mistake in the work. They did not pick up that factor of 2 from the combination of these two terms. And so they blew it in that sense. But it's important to realize if you just thought that was crazy, like look at how much work that was. That's a hell of a lot of work. You have 100 seconds to answer this question. You got to remember some test-taking strategies here. It says, what is the magnitude of the change in potential energy of the spring block, the block spring system when it travels from its lowest vertical position to its highest vertical position? The spring is going from the most stretch to less stretch. It's not going to be 0. Now, as it turns out, 0 is the overall change. Whatever amount of elastic potential energy it loses, it gains gravitational potential energy. And as it turns out, it's the exact same amount. But it's not going to be 0 because there's no gravitational potential energy considered for this system. That's out. Now, notice B is an equation that takes the form of a potential energy equation. That's not going to be right because potential energy is not part of this. Now, it's weird because C is the only term here in the answer choices that doesn't look like a potential energy equation. But notice 1/2 K naught L1 plus L2 squared is the potential energy at its highest point. Here it's asking for the change. And if we're trying to find the change or the difference between two values, and this is just showing one of those values, that can't possibly be it. And so because it can't be A, B, or D, if you really think about it, then the answer has to be C. Now, that video was a little longer than I wanted it to be, but I think this vertical spring question is one of the more confusing questions. And so I want you, to really pay attention to these things, and I hope you got something out of this here because I know these kind of questions can be confusing. All right, everybody, take it easy.